In these slides, we're going to see what happens when you put a material, a dielectric material, an insulating material that consists of polar molecules. So polar molecules, as we've seen before, they are already polar without having an electric field being applied to them. So this is an example of a material that has polar molecules, and initially, before there's an electric field, the molecules are oriented randomly. So let's say you get a capacitor. This is one plate of the capacitor with positive charge. This is another plate with negative charge. We're looking at the cross section. So the capacitor plate comes out of the page. And then there's an electric field, E node, between the two capacitor plates. And during the process that we're going to talk about, we're going to keep the charge on the conductors the same. It never changes because we're not going to connect the conductor to anything else. So if we have this region where there's an electric field now, when we insert the dielectric that consists of those polar molecules, what happens? We've seen before, when you put a dipole in an electric field, what happens? The dipoles orient along the electric field direction. They don't necessarily have to be pointing exactly along the electric field direction, but they point more along the electric field direction because there are always random movements of the molecules. They never stay in one specific position. They're always constantly moving. But there's an alignment of the molecules in the direction of the electric field. So the positive charges want to be more along the electric field. The negative charges want to be away from the electric field. And this alignment gets bigger when the temperature is lower or when the electric field is larger. So let's look at the charges between the positive charges here for these molecules and the negative charges for these molecules. Of course, I've drawn here only 9 molecules in total, but of course there are millions and millions and millions of molecules inside the material. So these two charges actually, these two positive and negative charges are actually very, very close to each other. They're almost on top of each other. So the total charge in this region, the positive is almost right on top of the negative charge. So this material actually is neutral in the middle. The same thing happens with this positive and this negative and this positive and negative. All the charges in the middle of the material, they cancel out with the other charges right next to them. But if you look at the charge that's on the edge of the material, and imagine this charge is located right on the edge of the material, well, these negative charges don't have any other positive charges of the material to cancel them out. So you get some negative charge sticking out of the material on the left side. And on the right side, you have some positive charges sticking out also of the material. There's no other negative charge of the material itself that will counter these positive charges. So you get some positive charge sticking out on the right side. So it's as if you have a sheet of negative charge, induced charge on the left, and a sheet of positive charge induced on the right. And of course, this sheet of positive charge and this sheet of negative charge will make their own electric field pointing to the left, the induced electric field. The induced electric field is opposite the original electric field. So now the question is the total electric field inside the material, if you go to any point inside the material, is the total electric field smaller or larger than it was before, or the same? Of course, the electric field is smaller because the electric field is now E node minus E induced. It's the sum of the electric fields, but one is opposite the other, so the electric field gets weaker. It's E node minus E induced. So what happens then for the potential difference between the two plates? Well, if the electric field got weaker, then the potential difference will get weaker because the potential difference is proportional to the electric field. So it turns out then in this situation, the charge on the plates, this charge and this charge hasn't changed during the process of inserting the dielectric material. This Q stays the same, but the potential difference has become smaller because the electric field became smaller, because of the alignment of the molecules, because of these molecules sticking out, positive charge sticking out, because of these negative charges sticking out. So if this stays the same and this gets smaller, then what happens to the capacitance? Then the capacitance gets bigger. And so this is the intuitive understanding of why the capacitance will increase if you put insert a dielectric material that consists of polar molecules between the capacitor plates.